Well, thanks a lot to Susanna for inviting me. It's really great being here tonight with all of you. And thanks a lot for the kind words about Keras. I'm really glad it's useful. To introduce myself beyond what Susanna just said, I work at Google as a software engineer. I work on TensorFlow, so Google's machine learning platform. And on the side, I also do research in AI. And my interest is specifically in understanding abstraction, reasoning, and how they work in the mind as the chemical artificial minds to go after abstraction. And 4 years ago, I started Keras, like I said, deep learning framework. And we're going to be celebrating the 4th birthday of Keras in 1 week, so it'll be 4 years. And Keras is one of us. And I've also written this book about deep learning. It's an introduction to deep learning for software engineers. It's a edition as well. And the contents of my book is mostly technical. If you're already familiar with the book, you will see some of it some edition. And so my talk is about the future of deep learning. So perhaps vague topic. As you all know, currently we're in this very hot AI summer, I would say, of intense interest and hype, where we have a lot of funding, corporate funding, academic funding around AI. Actually, if you look at the history of AI, deep learning is still a very new trend. Just a few years ago, very few people believed in deep learning. And now we've used this to achieve these amazing successes on historically very hard problems, machine perception, computer vision, and even natural language processing. So is this going to last? Is this trend going to last? Will deep learning eventually lead us to human-level AI if we just scale it up to more layers and more training data? So that's the goal of my talk, to try to answer this question. So I'll be trying to zoom out a little bit to look at what deep learning really does, what it really is. Look at what it attracts and some of its limitations, and to try to see the road ahead for AI. In particular, try to see the road up to human level AI, like which hills we're going to have to be climbing to get there. So I've been sketching out architectures for human level AI, strong AI, for about a decade now. I made a lot of progress around 2010. I came to Todai right here as a student in 2012, and I was doing exactly this research. So these 2 pictures are taken from a presentation about my research that I did here at Todai in April 2012. So it's been quite a few years now. And the ideas I was playing with at the time are things like reinforcement learning, hierarchical reinforcement learning, the intrinsic motivation of curiosity, learning these deep hierarchies of modular features to encode the system motor space, and learning them by using information compression, the sort of learning engine. So these are all fairly modern ideas that probably wouldn't be out of place at UNIPS in 2019. And the way I saw it back then, it seemed really like we already understood all the core building blocks to build human-level AI, and all we needed to do was to bring them together into one coherent picture, into one coherent framework, and then just figure out small implementation details, like how to turn it into an algorithm. That should be fairly straightforward, right? Well, it turns out, although none of these ideas were wrong, they actually turned out to be pretty interesting. And some of them even profound, and people are still looking at this stuff today. But despite that, they were definitely not sufficient. It turned out the small implementation details were actually quite critical. So let me tell you, human-level AI, honestly, it turns out to be a lot harder than it seemed to me in 2010. And I'm definitely not the first one to notice this pattern. So most of you probably know John McCarthy. He was one of the early pioneers of AI. He's actually the one who coined the term artificial intelligence in 1955. And so I was doing this very early AI research in the 50s and the 60s, and along with his colleagues, like people like Marvin Minsky, he really believed that human-level AI was right around the corner, that we already understood all the core building blocks, and that's all that was left to do is basically scale it up. Buy a faster computer from IBM, and just run the same algorithms at scale, and maybe in the process figure out some very tiny implementation details, like how do you encode knowledge and reasoning in a computer. Should be pretty straightforward. So turned out this was actually harder than expected, and they understood less than they thought they understood. In just the same way as 10 years ago we were actually understanding a lot less than what we thought. And so this is an actual quote from John McCarthy from 2006. Human-level AI is harder than it seemed in 1955, and I think that's still true today actually. These things are actually pretty hard. I mean, technology is hard. When we started experimentation, we actually had a very hard time setting up the display, and now we have this UI bar that's still there. So that's about the stage we're at. But yeah, let's try to get to human-level AI. So remember this picture. What I'll be trying to do in this talk is basically zoom out, look at the road that we're on, look at where we came from and where we're going, and try to figure out what the road ahead looks to eventually achieve perhaps human-level AI. So we are going to be talking a lot about deep learning, about the limits of deep learning in particular. So it's good to spell out exactly what we mean by deep learning. So what's deep learning? It's not this. This is how deep learning is usually illustrated in the media. There's a lot of hype around deep learning these days. And this hype serves to obfuscate what deep learning really is. In particular, when people love to compare deep learning to what the brain does. So this hype really gives deep learning an aura of mysticism. And I don't think that's a good thing. The truth is deep learning has very little to do with what the brain does. Deep learning is more like this, right? You know about it, right? A deep neural network. It's like this parametric model that you fit to some data. And it's differentiable and you fit it with grand descent. So, to be honest, maybe this is not a fair picture, because we are talking about very, very large parametric models that are fit to many, many data points, and that are structured in a particular way so as to induce these hierarchies of modular features. So that scale makes a difference for sure, but it's not such a big difference. So the nature of deep learning is still very much the same nature as linear regression, right? And definitely not the same nature as our mind. And honestly, to me, that's the most surprising thing about deep learning is how simple it is, right? Just a few years ago, very, very few people, basically no one, believed that we were going to achieve the results we've achieved in computer vision, in image perception, by using this extremely simple idea, just very large parametric models trained on many, many samples. So when I was at TODA in 2012, when I talked about deep learning, people looked at me like I was crazy, because neural networks, we had tried that already. Neural networks were a failure, and everyone knew that. And even the people who did believe in deep learning and the potential of deep learning, and there were not that many of them, even them, they did not expect the solutions to be so simple. If you look at a lot of the earlier deep learning research, a lot of the ideas are actually quite advanced. People really believed things like, in order to make deep learning work, you need some other optimization, like patient-free, some other optimization, or you need layer-wise pre-training, and so on. It turned out you don't really need any of this. It's really that simple. It's really, the only thing you need is these very, very large parametric models that are structured in an extremely simple way, trained on a lot of data. So this really simple idea can work extremely well if you just scale it up. And that's really the lesson I'm learning from, is that you can have this extremely, like, almost trivial idea, and if you scale it up enough, it's going to get results that you really did not expect. So in deep learning, everything is a point in a vector space. So everything is a vector. When you solve a deep learning problem, you start with some raw data, it could be images, text, video, sound, and so on. And the first thing you do is that you vectorize it. So you turn it into this input vector space. And then this input space is going to be mapped point by point to a target space. Basically a bunch of target vectors, typically labels. And this point-by-point mapping is done via a stack, a series of so-called layers. And a layer is basically a very simple geometric transformation from one intermediate vector space to another intermediate vector space. And most of the time, one layer is an affine transform followed by some squashing function, typically a ReLU. So it's a very, very simple geometric transformation, but together, the chain of layers forms a very complex geometric transformation that's broken down into this series of very simple ones. And an important characteristic of this transformation is that it must be differentiable, because you're going to find its parameters using gradient descent. And intuitively, differentiable is going to mean that it has to be smooth and continuous. And that's actually a huge constraint. So you can visualize this process in 3D if you think about uncrumpling a paper board. Like if you have a crumpled board of paper, that's your manifold of input data. And if you want to flatten it to give it back its original structure, what you're interested in, the way you're going to do it is by applying a sequence of very simple finger gestures. And each gesture you're applying is, it's like the operation of one layer. It's almost like an affine transform. So it's very, very simple. But together, this sequence of transformations forms this very complex unfolding sequence, right? So you can say that deep learning is kind of a mathematical machine for uncrumpling very complicated manifolds of high-dimensional data. And really, there are no limits to the complexity of problems that you can solve with this very simple approach. It can scale to arbitrary complexity, but there's a catch. There's a catch, right? The catch is the amount of data you need. In order to solve a problem with a deep neural network, you're going to need a dense sampling of the problem you're looking at, a dense sampling of the input across output space. And that's expensive. So you can scale this technique, like deep learning, differential programming, however you want to name it. You can scale it to arbitrary levels of skill, arbitrary levels of competence, beyond human level if you want. But it has a cost. It doesn't scale very well. And of course, there are diminishing returns as you climb up the skill spectrum. For instance, if you want to learn to play chess with deep learning, chess is a good example because there are very few human priors involved in playing chess. Chess doesn't really look like anything from your life. So you have to learn it pretty much from scratch. And a human can get pretty good at chess in like a few hundreds of games. But the deep learning model, to get to that level, it's going to need hundreds of millions of games, right? So it's really not the same scale. It's just not very efficient. And if you want to achieve superhuman chess playing abilities, well, of course that's possible. You can, honestly, you can achieve arbitrary levels of skill with this very simple technique. But it's going to cost you. It's going to cost you, hundreds of billions upon billions of games, simulated games. So deep learning has these stark limitations, and these limitations are really manifestations of how deep learning works. So for instance, deep learning is extremely sensitive to any sort of small change in the inputs that wasn't featured in the training data. So deep learning models can only make sense of things they've seen before. So effectively, they are template matching algorithms. They can match templates of arbitrary complexity. They can emulate arbitrarily complex behaviors. But it's still just template matching. And that's pretty well documented in the literature, but also in practice, of course. I'm sure most of you have played with deep learning before, and you must have encountered that. Sometimes your models are going to break down in really weird ways. And I think a very big risk with deep learning is to anthropomorphize them, so to misinterpret what these models are doing and to overestimate what they are doing. Because we as humans, we have this tendency to project beliefs and intentions on the things around us, right? Like if you draw a smiley face on a rock, then the rock becomes happy. And applied to deep learning, that means that when you get a model to perform something that's normally done by a human, like labeling images or captioning pictures, then you are led to believe that the process that goes on inside this model mirrors the process that goes on inside your mind when you do the same thing. But that's actually not true at all, because the problem that the deep learning model solves and the problem that you solve when you do the same thing, like captioning pictures, they're actually two completely different problems. If you take image classification, for instance, the labels in your image classification problem, they are all very much constructs that come from human experience. Things like cloud, tree, and so on. They are abstract concepts that emerge from our embodied experience as human beings. And deep learning models have no access to this stuff. They have no grounding, right? So the process through which you develop these machine learning models is that you start with the world, and then you add humans in it, with their specific sensory motor space, and humans, through this embodied experience, they will develop these concepts, and then they will create data sets where they're going to be mapping, for instance, grids of pixels with abstract concepts. And the abstract concepts, like the concept of tree, the concept of cloud, they are not properties of the real world. They are very much human projections. If you were an octopus, for instance, you would be coming up with very different ways to parse the world, to look at the world, and you would be creating data sets or machine learning models that would look very different, right? What kind of machine learning model would you train if you were an octopus? I don't know, but it's very interesting. And the machine learning model has no access to any of this stuff. It's just looking at its input space, at its target space, and it's just learning this point-to-point mapping using gradient descent, right? Using this smooth differentiable geometric transform. And that's a very, very different task than what you're doing. And it becomes very apparent when your model is exposed to something that was slightly different from its training data, and suddenly the model just makes no sense whatsoever, because the process through which the model was performing the task is really completely different from the process that's going on in your own mind when you do something. So that's something really, really important. So yeah, so deep learning is really just pattern recognition. And it's really, really good pattern recognition. But at the end of the day, that's really the only thing you can do with differentiable programming, which I think, by the way, is going to be the term, is map this input space X to this output space Y using this smooth continuous geometric transform. And so to be clear, I'm not trying to downplay the profound significance of deep learning. Being good at pattern recognition is actually immensely useful. The scope of problems you can solve if you're good at pattern recognition, even if you're not very efficient in the way you learn these models, it is immense, right? I'm sure you guys are doing like amazing things with deep learning. There are so many problems we can solve today just using these algorithms. We don't need human-level AI to change the world with machine learning and AI. So I'm really not trying to downplay the importance and the usefulness of deep learning. And deep learning absolutely does have a very important place to play in the future of AI. But it definitely has its limits. Deep learning does not solve AI, because deep learning is pattern recognition, and AI intelligence is not pattern recognition. So yeah, we're not gonna get to human-level AI just by adding more layers and training on more data. So this difference really brings us to the fundamental difference between human capabilities and the capabilities of deep learning models. Deep learning is really only capable of local generalization, which means that it can only make sense of inputs that are very, very close with what has been trained on, what they've seen before, right? Which is why if you want to train a very good deep learning model or a superhuman deep learning model, you're going to need a dense sampling of the task it's doing. So if you want to play chess at superhuman level, you're going to need billions and billions of games. And on the other hand, humans can cover a lot of ground using very few data points, right? That's what I would call extreme generalization. And this extreme generalization is really enabled by abstraction and reasoning. So to really understand this difference, we can look at a couple really simple examples. So let's say you have this problem, you're trying to get launch parameters to land a rocket on the moon. If you were to use deep learning to solve this problem, right? Well, first of all, you need to hard-code the search space. Like deep learning means a search space. So you're probably going to have to hard-code a simulation of the rocket. And then you're going to have to learn this point-by-point mapping between configurations in your search space and outcomes. Did the rocket get to the moon? If you're using something like reinforcement learning, like deep reinforcement learning. And you're going to have to launch your rocket like millions and millions of times to finally learn a model that works. And what's important is that eventually you will find this model, no matter how complex the problem is that you're trying to solve. There's no cap on the level of scale that deep learning models can achieve. But it's just not a very efficient way to do it. And humans, on the other hand. So humans, to start with, are very open-ended because they came up with the idea of going to the moon in the first place. Deep learning did not come up with this idea. The way we did it is by developing these very abstract models of the problem, what we call rocket science. And then we're able to adapt these abstract models with very few trials, right, with very few launches. So it's an extremely data efficient setup. Another simple example is, let's say you have a robot and you're trying to teach it not to get hit by cars in an urban environment. Well, if you're going to train the brain of your robot with deep learning, well, you're going to need to learn this dense mapping between configurations in the sensory-motor space and outcome. Did the robot die or not? And you're probably going to have to do that in a simulation because in the real world it will be completely impractical. And you are going to have to die millions and millions of times in order to learn good behaviors, right? Because it's a very complex problem. And every situation, every day is almost a new situation. And that's because you can only learn from direct experience, right? You need this dense sampling of almost every possible situation you can be experiencing. And humans, on the other hand, humans are quite remarkable because typically humans learn to not die, avoid getting hit by cars without dying even once. And that's really amazing. That's because we can learn from much more than direct experience, right? You can learn about death without dying. That's quite amazing. We can learn from instructions, for instance, from imitation, and so on. And that's really enabled by the power of abstraction of the human mind. Humans can learn things that they have no direct experience of. So, yeah, just adding more layers and training on more data is not going to get us to this extreme generalization. It's not going to get us any closer to solving AI. So we're going to need fresh ideas to overcome these limitations. But now that we're starting to see what the limitations are, then we're starting to be able to figure out what comes next. So how do we move forward from that? How do we achieve extreme generalization? So I think we're going to need three things. So first of all, we're going to need better metrics and better benchmarks. Then we're going to need richer models, like that go beyond stacks of fine transforms. And finally, we're going to need stronger priors and greater reuse across different models. So let's take a look. So first of all, I really believe that you cannot make progress on a problem, especially this kind of extremely ambitious, extremely difficult problem, if you don't have a good way to measure the progress you're making. And honestly, I think very few of the existing benchmarks in machine learning today are trying to measure intelligence. Mostly, people are focused on measuring skill, on measuring the capabilities of these models, but not really their power of abstraction or their power of generalization. It's their intelligence, it's really just skill. So I think we need an ambitious new benchmark that would be focused on measuring generalization, focused on measuring abstraction in machines, but also in humans, that you can start comparing the intelligence of machines and the intelligence of humans, like an IQ test, a GQ test, a generalization quotient test of sorts. Because intelligence, I think, is not a measure of skill, it's a measure of efficiency. It's a measure of the efficiency with which you acquire skills, right? So if you want to measure it, you're going to have to look at skill, of course, which is expressed intelligence, but you're going to have to normalize it by taking into account experience and priors, right? So let's say you're learning to draw, for instance. Well, if you're average, if you're an average person, maybe it's going to take you 10,000 hours to get really good at drawing. If you're really smart, maybe it's only going to take you 500 hours. And if you're a deep learning model and you're learning to draw well, you're going to have to practice each drawing you want to be able to make hundreds and hundreds of times with strong supervision. So it's not too great. So if you're just measuring skill, you're not really measuring anything interesting. So for instance, it's not intelligence to be superhuman at, say, playing StarCraft or playing Dota, because we already know that deep learning can handle arbitrarily complex problems if you just give it a dense sampling of the problem you're trying to do. So if you tell me, hey, we're superhuman at StarCraft, I'm just like, cool. So you finally, train on enough data. You like consume probably the electricity of a small city for 6 months. Congrats. So I think it would be much more interesting to look at how fast these systems can learn to pick up a new game, or how fast these systems can adapt if you change the rules of the game. Like for instance, you train a model on StarCraft 1, can it play StarCraft 2? Because if you're a very strong StarCraft 1 player and they give you StarCraft 2, lots of things have changed. It doesn't look the same, it doesn't play the same. But if you were a strong player, you will still be able to play StarCraft 2 pretty well, and you will become a strong player in maybe a dozen of games. Or like if you're trying to learn to play Dota, well, being superhuman at Dota is not super interesting, but I would be really interested to see how such a model could handle, for instance, being given a new Dota character, right? Like if you're a very strong Dota player, and I give you a completely new character you've never seen before with different skills and a different strategy in the alignment. If you're a very strong player, you can master it like in one shot, pretty much. A deep learning model is going to be completely lost. So yeah, I think we really need to break up that mindset that intelligence is skill and only measuring skill. We really need to be measuring generalization. We really need to be measuring abstraction and intelligence. And if we're not measuring it, we're not going to be making progress. And the second thing we need is we're going to need richer models. Because technically there are already AI systems that are capable of abstraction and reasoning and so on. And these systems are all currently hard-coded by human programmers. There are things like software involving search, planning, graph manipulation, formal logic, and so on. And these algorithms are what used to be called symbolic AI, back when AI didn't refer primarily to deep learning and machine learning. So I think we're gonna evolve towards machine learning models that will increasingly look like computer programs, like the sort of computer programs that humans are writing today, and not just these big, smooth and continuous morphings from one vector space to another vector space. Because here's the thing with deep learning. Deep learning is really useful because you can use it to programs that you couldn't actually develop by hand, right? That's what makes it, makes it amazing. It opens up, all these possibilities. But at the end of the day, if you look at the space of programs that you might be interested in, well, most of them cannot be expressed, cannot be learned as a stack of fine transforms, right? Even if you're trying to learn to sort a list using deep learning models, that's almost impossible, right? So most interesting problems just cannot be expressed with a deep learning model. So if you're using deep learning, you're actually restricting yourself to this extremely, extremely tiny slice of program space. And sure, it's a useful slice, but it's so tiny. So we are going to need to extend the hypothesis space of machine learning models to expand our search space. In particular, these models are going to start being increasingly like the sort of programs that today we are writing by hand. So programs that manipulate abstract models of what they are doing through things like data structures and so on. But of course, we are still going to be including differentiable programming in our models. So learning in machine learning in the future is going to be increasingly referring not to just tuning the parameters of a hard-coded differentiable geometric transform. It's going to increasingly refer to a search process that outputs discrete programs, right? Program synthesis. And in the process of going there, we're going to have to figure out, we're going to have to develop learning engines that go beyond backpropagation and stochastic gradient descent. But of course, that doesn't mean that we're going to throw away deep learning. Like in this visual graph, you can see, deep learning is still very much part of the big picture. It's part of the future of AI. So we're not going to throw away deep learning, and why would we? Deep learning works so well in the cases where it's applicable. It's actually a lot of cases, and sure, it's not super efficient, but you need to be efficient in order to be useful. And I love deep learning, and you guys, you all love deep learning, so we're not going to throw it away. Deep learning serves a very, very clear need, but we need to be aware of its limitations. So I believe we'll start developing AI systems that will be hybrid systems, that will blend together the capabilities of deep learning, things like pattern recognition, basically geometric intelligence, and the capabilities of old school symbolic AI, abstraction reasoning. Because if you think about it, what you would call symbolic intelligence, if you think about it, they are very complementary. Deep learning, geometric intelligence, provides you with things like intuition, being able to intuitively understand, for instance, a chessboard position, and also things like perception. And in general, pattern recognition. Pattern recognition is super useful. It's a key component of intelligence, obviously, but it's just one component, right? It is not the same as intelligence. There's a bigger picture. And meanwhile, symbolic intelligence provides you research, planning, reasoning. So they are very, very complementary if you want to build strong abstraction machines. And we have already lots of early examples of this. The most powerful AI systems today are actually hybrid systems. Like AlphaGo, for instance. AlphaGo is a combination of a deep learning module to analyze the board position and predict the next move, together with Monte Carlo research, which is very much symbolic AI. And another good example is self-driving cars. Self-driving is a tremendously difficult problem, and you could definitely not solve it with an end-to-end deep learning model, because you're running into the same problem as we had with inter-robots, learning not to get hit by cars. The situation space is just way too large. It's very easy to learn things that are basic things like automatic steering that works in 99% of the cases. But that's not driving. That's actually only the easy part of driving. So self-driving cars today are manipulating explicit abstract models of their surroundings. In this case, it's a literal 3D model, right? This model is, of course, handcrafted by human engineers. But the way it interfaces with the real world is through these perception modules, that connect sensors to the abstract model, that allow the abstract model to update itself. And these modules, they're all deep learning modules.
So Cybernetica is very much a hybrid AI system that's blending geometric intelligence with symbolic intelligence. And right now, we need to keep in mind that these systems are designed and coded by humans, right? Only some very small submodules are learned from exposure to data. But in the future, as we expand the capabilities of program synthesis, systems will be actually trained end-to-end, or more accurately will be formed through a search process, starting from high-level algorithmic primitives. So here's how it will work. If you have a new task, right, let's say you have Go playing, you will have a search algorithm, like a program synthesis algorithm, that will basically be capable of assembling primitives. Things like, hey, we're going to use a countnet because we have this grid of pixels to analyze. And we're going to use Monte-Carlo tree search because we have this branching decision process. And so it would combine these primitives into a solution program. And the top level complexity of this solution program would be fairly reasonable, right? That's what makes it possible to find it through search process. But because it's going to be reusing these deep learning subroutines and these algorithmic subroutines, the total complexity of the program is actually going to be very high, right? And such a system would be learned end-to-end, just from exposure to very few data points. So if we follow this vision, right, and machine learning models get more complex, more program-like, and they're built on top of these rich algorithmic and geometric primitives, well, then we are going to need more reuse, more sharing across different models, across different tasks, right? Because currently what we are doing with deep learning is tremendously inefficient, right? We are typically retraining a new model from scratch every time we have a new data set, right? But in fact, most data sets do not contain enough information to really solve the problem. So you need to share information with the solutions that you found in previously encountered problems. So that means we're going to need stronger priors. That's what priors mean. It's all these small submodels that you've accumulated over your lifetime. And we do this with lifelong learning, right? And one way to think about it is, for instance, you do not learn English from scratch every time you open a book in English, right? When you open a new book, you're actually reusing your knowledge, your pre-existing knowledge of language. And in fact, not just your knowledge of language, you're reusing the entirety of your knowledge of the world. You're using your world model, right? And you're doing that every time you're approaching something new. With every new task, you are bringing with you this accumulation of the models that you've trained on prior problems, right? And there's already a few non-biological settings and a few non-biological constructs that are implementing lifelong learning and abstraction. And one good example is software engineering. In software engineering, it is very, very common that you are reusing a submodule that was developed on a completely different problem. So if you think about modern software engineering workflows, when an engineer solves one sub-problem, like parsing JSON, for instance, what they will do, they're smart, that they will package the solution in a way that's abstract and reusable. And by the way, abstract literally means reusable. Something is abstracted if and only if it can be applied on a bunch of different inputs. And then once you have this reusable abstract package, you will upload it somewhere. You will put it on GitHub maybe, or you will put it on a package manager. And once you do that, then other engineers can search for it, find it, and fetch it, and then insert it into their own program, which was solving a completely different problem. Maybe your JSON parser was developed to build a web application, but now you're using it in a deep learning framework, for instance, right? And this really enables software engineers to solve problems that are way more complex than if they had to reinvent the wheel every time, right? Because the top level complexity of the programs we're creating stays very manageable, stays very small. But because you're reusing all these abstract sub-values that were previously developed, the total complexity of your program is actually immense. Like, you know, if you're writing something in Keras, for instance, you're not actually managing a lot of top-level complexity yourself. But the total complexity of your coding is very, very large because you're going to have Keras, you know, calling TensorFlow, calling QNN, and so on, right? And this is really a kind of abstraction which I think is the holy grail of AI, and I really believe that AI is going to move in the direction, right? And this would take the form, I think, of a meta-learning system that would have access to a global library of subroutines, of primitives, some of which would be deep learning primitives, some of which would be algorithmic primitives. And this meta-learning system, when faced with a new problem, would be capable of identifying which existing subroutines are relevant to solve it, would fetch them, would recombine them through a program synthesis, you know, search process into a program where the program, you know, its top-level complexity stays very reasonable, which is why you can actually solve it. And then when this meta-learning system finds itself generating a subroutine, which seems to be used in fairly similar forms for different problems, it would be, hey, it would say, you know, let's abstract it, let's turn it into a form where you can actually use the exact same program in these different settings. And once this subroutine is abstracted, the meta-learning system will just push it back to the global repository so that it can be reused either by a different meta-learning system or by the same meta-learning system at a different time. And if you do this at scale, if you scale it to, you know, millions of useful subroutines structured in a very nice and searchable way, and if you scale it to millions of different tasks, what you get is a system that can assemble a new solution program that will have a low top-level complexity but a very high total complexity that can solve basically anything using very few trials, using very few data points. So I think that's really the long-term vision for the future of AI and how we move beyond deep learning. Deep learning has all these great successes, but I'm afraid we're going to start hitting a wall, because sure, we can always scale it up, and if we scale it up, we're going to get better results. We're going to achieve higher levels of skill on specific tasks, but that's not really what intelligence is, right? So yeah, I think AI is going to really move in a direction that will make it more like software development workflows today. So if you want to know how AI will operate in the future, you can look at how human engineers operate today, because AI is very much the art of program generation, right? And we already have existing non-biological systems that are extremely good at generating programs. They actually do run on human minds, but in a very distributed way. And I think software engineering and things like open source communities are very much this kind of like non-biological proto-strong AI. And of course, science, the scientific community itself, is general purpose problem-solving process that is non-biological, even though it does run on human minds, and that is extremely powerful. That is in fact completely superhuman, right? So I think if you want to know what AI will look like in the future, you can look at these systems, at science, at software engineering, and so on. Yeah, so of course, it's easier said than done. The implementation details, are quite tricky. I think we will probably be looking back on these ideas in a few decades, and we'll be like, human level AI was, harder than we thought in 2019. But yeah, so remember, we're going to need better metrics, better benchmarks that focus on measuring intelligence and not the skill. We're going to need richer models that are more like programs and less like just stacks of fine transforms training squared understands. And we're going to need stronger priors through lifelong learning together these huge libraries of reusable components across problem domains. And AI will be more program synthesis than just linear regression, just fitting the parameters of the big model. And this program synthesis workflow will probably closely resemble current software engineering workflows. So that's the long-term future. So that's it. I guess we can